Okay, today, guys, we're going to go over 3B, putting numbers in perspective. And basically, we're going to do a little bit of scientific notation in this section, and then a little bit of error. In the next section I'm going to cover, we're also going to go into significant digits. And so there'll be kind of a lot of I don't want to say values that we're going to work with when we do the statistics section, but it will come up when we do the section on statistics. I believe it's chapter 5 or 6. I'll have to go back and look at that. But so the first thing we kind of want to talk about is scientific notation. And again, scientific notation is exactly what it sounds like. A lot of times in science, they talk about atoms and molecules and distances to the sun and, size of these giant, celestial bodies and, very small values, very large values. So these scientific notations kind of designed so we can work with these really big numbers without having to rewrite the really big numbers over and over again. Okay, so scientific notation is a format in which a number is expressed as a number between 1 and 10 multiplied by a power of 10. And notice it says between 1 and 10. I normally, you basically have from 1 to 9. If it's a 10, then you need to add another value to the power of 10. So it says, for an example, we have 6. Let me make this a little bit bigger. So for example, this is what, 6,700,000,000 in scientific notation. So what you do is you write one number to the left and you put a decimal. So there will always be one number only to the left of the decimal, and then you put the rest, okay? But you only put the values that you have. And again, we're going to talk about significant digits later on as well. But all these other zeros right here, I'm going to be able to represent with powers of 10, because remember, something times 10 is just, 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is 100,000. All you're really doing is adding a 0 to a number when you're multiplying by 10, because we're in the base 10 number system. So what I'm going to do is I'm going to do 6.7 times 10, and now I have to count how many places it's going to take to go from here to here, okay? So what I do, and again, it's a preference. There's also people that want to do it, a different way. What I do is I say, okay, I'm here and I need to end up here. So what I do is I say, well, this had to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would put times 10 to the 9. Remember, when going from bigger to, so we're taking a really big number and writing it small. Use positive powers of 10, okay? When going from small to bigger, like in the next example, use negative powers of 10. So here we went from a really big number and rewrote it as a small 6.7. Well, that means that we needed a large power of 10. So times 10 to the 9th. And again, all this is saying, you guys, is once again, is we're doing 6.7. And now 10 to the 9th means I go 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I put zeros in all of these spots. Now, and then I put a decimal. Now this better be the same number that we started with over here. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 zeros in both of them, so we're good, okay? And again, this is a certain type of notation that they want you to use, okay? So now we're gonna go the other way. Now we're starting from, look how small this number is, 0.00002. And then they wanna write it as 2.0 times 10 to the negative 50. Oops, I already have the answer here. Sorry, I forgot to delete that. So what they did was they wrote 2.0, okay? And then they did times 10, oops. And then they counted. They said, okay, this number here has to end up looking like this. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So it took 15 to get that decimal right there. Okay. But the thing is we're going from a smaller number to a bigger number. So instead of using a positive, I'm going to use a negative 15th power. Okay. So what this would do, if I wanted to rewrite this, and this is oftentimes referred to as decimal notation or standard notation, and this is written as scientific notation. So this is, so what I'm going to do is I'm going to do 2.0, and now I'm going to go, so remember, a negative exponent tells you to go left. A positive exponent, go right with the decimal, okay? So here's my decimal, and I'm going to go left 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you guys get it, and this number will now match the same. So scientific notation is rewriting things the same as they already were, but now look at this number versus this number. Which one's going to be easier to write? Look at this number versus this number. Which one's going to be easier to write? So that's what we're working with here. Scientific notation is trying to make it easy on us when we deal with very, very large numbers or very small numbers. Okay, so giving meaning to numbers, perspective through estimation. An order of magnitude estimates and specifies a broad range of values, usually within 1 or 2 powers of 10, such as in 10,000s or in 10 millions or in the millions, okay? So it says here, order of magnitude of ice cream spending. Okay, so it says, is the total annual ice cream spending in the United States measured in thousands of dollars, millions of dollars, or billions of dollars? So I just left this one already completed because I wanted you to think about it. So they say, suppose that the average person consumes like 50 servings of ice cream per year. So they want to see how much the entire United States, right? So that's, remember, the annual ice cream spending in the United States. Now, I don't know the exact numbers on the United States, but I know it's like 300 million or 350 million or something like that. So that's what this number is here. This is their estimate for how many people are in the United States. This is $1 per serving, and this is servings per person, okay? So what we're doing is we're gonna do 50 servings per person times 1 times 3 times 10 to the 8th people, okay? So when you do this, let's see here, is the total annual ice cream in the United States measured in thousands of dollars, millions of dollars, or in billions of dollars? Reasonably guess that the average person has something like 50 servings of ice cream per year. So 50 servings of ice cream. So they, personally, I think they should have wrote the 50 here. So 50 servings divided by person per year, okay? Or times years. So now we know that the denominator now has, you know, years in it, right? So this is going to be per year. So we're okay with that. Now, let's see here. Did they tell us the dollar amount? They just said it's $1 per serving. I don't see that anywhere. But what I'm going to do is I'm going to do 50. So I'm going to take this over here, and I'm going to do 50 servings per person times years. Okay. Now we're going to multiply this. Oops. And we're going to do $1 per serving. They're just estimating that. And then they're going to do 3 times 10 to the 8th people. Okay. So now here's the thing. Servings and servings cancel. People and, I know it's not exactly the same, but you guys get the idea. People and persons cancel, right? So we're left with per year, and we're left with money. So what I'm going to do is this is going to be 50 times 3 times 1, okay? So this would be 150 times 10 to the 8th. Okay. Well, that seems like kind of a lot. Okay. So let me try to figure this out a little bit better. This is going to be 15, or no, but to be in scientific notation, it has to be 1.5, right? So how do we take 150 and write it as 1.5? Or I'm sorry, how do we take, I said that backwards. How do we take 1.5 and turn it back into 150? Well, we need to multiply it by 100. So I'm going to multiply that by 10 squared, right? Now, if we think about this, 10 squared times 1.5 is 150, but don't I still have this leftover times 10 to the 8th? So I have to multiply this by 10 to the 8th. So hopefully you guys remember back in the days when you guys first learned exponents and stuff, you have a same base of 10 to the 2nd and 10 to the 8th. And when you're multiplying, 10 to the 2nd times 10 to the 8th becomes 10 to the 2 plus 8, which is 10 to the 10th. So here we're going to get 1.5 times 10 to the 10th, okay? So that's where they got this right here, 1.5 times 10 to the 10th. And this is dollars per year, right? Oops. So all I'm doing is I still have my years left, I still have my dollars left, and I go with that. Now over here they say 1.5 times 10 to the 10th is approximately 15 billion per year. Now the reason they say 15 billion per year is they're trying to now talk about it in a way that we can understand. So here, if we look up here, it says, an order of magnitude estimate specifies a broad range of values, usually within 1 or 2 powers of 10, such as in the 10,000s or in the millions. So that's what they're trying to do right here, is they're trying to get it in to make sense with us. So we don't know the exact value, but we're estimating that it's about 50. Whoa, I don't know how to spell billion. So we're estimating, so this is the correct answer in scientific notation, but if you guys were talking to somebody, you wouldn't tell them, oh, this is how much we spend 1.5 times 10 to the 10th dollars per year on ice cream. If you wanted to talk to them about it, you would say we spend about 15 billion per year on ice cream. And also there's some estimates in here. The reason they have to say is we don't know the exact number of people in the United States. This is an estimate, and we're estimating that it's $1 per serving. It could be $2 per serving for all we know, or less or more. So that's why they kind of went with the approximately value. So this is in scientific. Okay, so this is in scientific notation. And then here, this is trying to help somebody explain it and understand using the order of magnitude. We're estimating how much it's going to be, okay? So this is just a little table that's in your book. I don't know if I saw one of these in the homework, but I definitely saw it in your book. So this is just kind of giving you a heads up on how things are. So it says energy released by metabolism of one average candy bar. So we have here energy in joules, 1 times 10 to the 6, okay? Energy needed for 1 hour of running, 4 times 10 to the 6. And remember, 4 times 10 to the 6, what does that really mean? That's 4.0, right? Times 10 to the 6. We could rewrite this as 1, 2, 3, 4, 5, 6. That's what times 10 to the 6 does, right? So this is actually 2, 4, 6. 1, 2, 3, 4, 5, 6. Yeah, so this is actually 4 million joules. This sounds a little bit off to me. 1.2, well, I guess, well, it just sounds like way too much, but I haven't taken physics in a while, and 4 million joules sounds like a lot. to run for an hour. So I'll have to look at that again. But something like this, the reason they want you to do this is they want you to see, okay, the energy released by fusion of hydrogen in 1 liter of water. Okay, so this is a nuclear reaction right here. So they're talking about this. So this goes 6.9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what this is trying to show you is if you were to write this out, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I don't even actually know how to pronounce this number. So this is thousands, millions, billions, okay, it's trillions. So 69 trillion joules are released, the amount of energy released compared to this. Now, 4 million sounds like a lot, but when you compare it to this, it's really no comparison whatsoever. So when you jump in powers of 10 and it's drastic like that, that is a big deal. So that's what they're trying to get you to see. I'm not going to test you on, can you reproduce this table or anything like that, but they're just trying to show you energy released by burning 1 kilogram of coal, 1.6 times 10 to the 9th kilogram. You know, it's a decent amount. We would have to do a conversion into pounds to see how much that actually is, or in terms of tons. But again, I just wanted to put this up here so you could see US annual energy consumption, 1 times 10 to the 20th. That is a massive amount of energy. World energy consumption as a whole, 5.3 times 10 to the 20th. So if you look at the comparison, we are both in the times 10 to the 20th. So at least we're in the same category in terms of amount of energy consumption, but that's just the US versus the whole world, okay? And I'm assuming if your book grabbed this data is probably somewhat accurate, so, and it's believable. So it says US versus world energy consumption. So compare the US population to the world population and the US energy consumption to world energy consumption. What does this tell you about energy consumption in the United States? So what we're going to do is we're going to say, well, world population, and this is an estimate, we got about 7 billion. Okay. But in scientific notation, this is 7 times 10 to the 9th. Okay. And then we have US pop. I said about 3.5 or 350 million. I guess they're going to say we're at 300 million. And we have 3 times 10 to the 8th. Okay. So if we do US over the world, that means that we're going to use 3 times 10 to the 8th divided by 7 times 10 to the 9th. So something that's really nice about scientific notation. So notice if you did it the other way, you would have to write this out. You would have to write 300 million divided by 7 billion, right? But what scientific notation does is scientific notation just says, well, this is 3 over 7, and then this is 10 to the 8th, and this is 10 to the 9th. So we're still left with 10 to the 1th. So this would be 3, 7 times 10 to the 1, but that's really just 3 over 7. Now, if they want us to use it as a decimal, okay, this is actually, let's see, what is this as a decimal? I think it is actually 0.0. Oops, no, I messed up. Hold on, you guys. Sorry about that. This is times 10 to the negative 1, because look, this is in the denominator. Remember, if you ever have your tens in the denominator, that's the same as, if you have 10 to the negative 1, that's the same as 1 over 10, right? If you have 10 to the negative 2, that's the same as 1 over 100. If you have 10 to the negative 3, that's the same as 1 over 1,000. Okay, so whenever you multiply something by a negative power of 10, you're actually multiplying it by 1 over 10, 1 over 100, 1 over 1,000, so on and so on, which means you're basically dividing. And sorry, I screwed that up. I'm sorry, I screwed that up right there. The 10 is in the denominator, so that makes it 10 to the negative 1. However, scientific notation doesn't really have fractions in it, so we have to convert this. So I'm going to do 3 over 7 on my calculator. And I get 0.42857. I get 0.42857 times 10 to the negative 1, okay? But let's round off to, well, let's rewrite it first. Because did they say they want the answer? They didn't say they wanted the answer in scientific notation. So if they just want it as a decimal, this would actually be 0.042857. So I'm going to approximate this. Well, I guess this is an approximation. And then I'm just going to say, you know what, let's approximate this to 0.043. Let's just round off. Let's use 3 decimal places for this problem. So I rounded off. I just looked at the 2. I'm sorry, I was going to round off to 3 decimal places. So the 8 tells me to round the 2 up to a 3. So I got 0.043. Okay, now this is not scientific notation. If I wanted it to be scientific notation, I would then have to write it as 4.3, right, if I round off, times 10. Now, how am I going to make this look like this? Well, I need to move the decimal 2 to the left, so that would be negative 2. So this would be the correct answer in scientific. This is the standard. Okay. Now, just depending on how the question wants it, you just have to decide which one to use. If I ask for standard, then you circle this one and give me this one. If I ask for scientific, then you give me this one. Okay. So this, even though it looks like scientific, it's not, because remember, scientific notation has to have only one number to the left of the decimal, one number to the left, right? One number to the left of the decimal. Okay, so let's see where we're at. Okay, and now we'll talk about scaling. So they can, you know, on maps, they can say, well, 1 centimeter is equal to 1 kilometer in real life, like if you were actually trying to walk there. So this is a 1 to 1,000, because we know if we do 1 centimeter, right, and we want to convert that to, no, we want to do 1 kilometer, and we want to end up in centimeters. So we would do, let's see here. Oh no, we didn't. I didn't teach you guys to do it that way. So we're just going to go km is here, and cm is here. Right. So km is here. So 1, 2, 3. So here's meters, and here's decimeters, and then here's centimeters. So we had to go from 1, 2, 3, 4, 5. So we had to go 5. So that's how they got 100,000, because this means the scale ratio is 1 to 100,000, because we had to go 1, 2, 3, 4, 5 to get to kilometers. Okay, so if you take 1 times 10 to the 5th, that would be 1. So 1, 2, 3, 4, 5. So all I'm doing is I'm just converting in my mind. How would I convert? How many centimeters is 1 kilometer worth? It's worth 1,000, right? So this is a 1 to 1,000 conversion. So it says the distance from Earth to the sun is about 150 million kilometers. The diameter of the sun is about 1.4 million kilometers. And the equatorial diameter of the Earth is about 12,760 kilometers. Put these numbers in perspective by using scale model of the solar system with a 1 to 10 billion scale. Oh boy. So this is going to be some writing. Okay, so let's see here. Okay, let me see here. Let's see, let's write scaled, oops. scaled Earth to sun distance. Let's do this one first, okay? So the actual distance divided by 10 to the 10th. Now, that's because if we wanted to write 10 billion, so that is millions, that's 10 billion, right? So this is, how would you generate this by doing times 10 to the what power? Well, this is 1, 2, oops, let's go this way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would take you 10 decimal places. So we're going to do 10 to the 10th. So that's where I got this from. Okay, so that's because they told me the scale is 1 to 1 billion. So all I did was I wrote 10 billion in scientific notation, which is 1 times 10 to the 10th. Okay, and I mean, we could do that. But realistically, 1 times 10 to the 10th isn't going to do anything, right? Because the 1 times anything is just what it started with. But I'll just write it for now, okay? So then the actual distance is 150 million kilometers, okay? So 150 million kilometers divided by 10 to the 10th. So what I need to do is I need to convert this 150 million kilometers into something easier to work with. So I'm going to write 1.5 times 10. So 150 million. So that means I need to go 1, 2, 3, 4, 5, 6, 7, 8. So this would be 1.5 times 10 to the 8th divided by 1 times 10 to the 10th. So remember we talked about this. This would be 1.5 times 10. Now, who's bigger? The bottom is bigger by how many? 10 to the 2. But whenever it's in the denominator, that means it's a negative exponent now, right? So this is completely gone. It becomes 1, and this becomes 10 to the 2, okay? So now we have 1.5 times 10 to the negative 2, and this would be kilometers, okay? Now, if we wanted, we could convert this to meters. If you were trying to explain to somebody, because everybody kind of knows a meter is about 3 feet, not quite exactly, or maybe not everybody knows that, but a meter and a yard are close to the same. It's not exact. So if I was trying to talk to somebody and I said this is 1.5 times 10 to the negative 2 kilometers, that doesn't help me as much. So what I'm going to do is I'm just going to say that this is 0.0015. Let's see. So that's 1, 2. That's too many. 1, 2. So 1, 2. So there you go. So this is 0.015 kilometers. Well, that kind of doesn't help me very much, but we know that kilometers, 1 kilometer is 1,000 meters. So what I'm going to do is I'm going to rewrite this in terms of meters, just so I can talk to somebody about it. So if I multiply this, so let's do a little note over here. Note. Or let's do recall. 1,000 meters equals 1 kilometer. So this is from our conversion section. So that means I have a kilometer right here. I can rewrite that as 1,000 meters if I wanted. So this would actually turn out to be 1, 2, 3. So 0.015 times 1,000 meters would equal, what is that, 15? So instead of telling someone that it's 1.5 times 10 to the negative 2 kilometers, that doesn't make a lot of sense. Or telling them 0.015 of a kilometer, that doesn't make a lot of sense. I could tell them, oh, it's about 15 meters, okay? And that's on the scale, right? We're not saying that that's the actual distance. We're saying using the scale of 1 to 10 billion, right? So if we wanted to use like a scale, like 15 meters is about 45 feet. So we could kind of use a football field to express it, you know, to try to show, or maybe like a playground or somebody's backyard, to show how far this actually is in terms of scale, okay? Then the next problem says scale sun diameter. Okay, so let me see here. This is, let's see. I feel like I'm missing something. Oh. Oh yeah, I think I skipped that one. Oh no, I did. So the slide 2 is actually the work we just did right now. So example of Earth and Sun. So the scale of sun diameter is the actual sun diameter divided by 10 to the 10th again. So we're using our 10 billion. Okay. So this time, the actual sun diameter, if we read the problem, 1.4 million kilometers. So we're going to say this is equal, I'll write over here so we don't run out of room, 1.4 times 10 to the 6th kilometers divided by 10 to the 10th. Well, this will actually work pretty good for us. This will be 1.4. Remember, this is going to cancel again. So this will cancel and this will cancel and be left with, oops, we'll be left with, this is 1, this is 10 to the 4th now. And we're left with 1.4 times 10 to the negative 4 kilometers. However, we know now that there's a relationship between centimeter and kilometers, right? We did that up here. So kilometers to centimeters is 1 times 10 to the 5th, okay? So we're gonna multiply this now by, let's say 10 to the 5th centimeters over kilometers. You could just do it in your head also. You could just count the place values. I'm just trying to show you what I'm actually doing because I'm going to cancel kilometers here. So this would become 1.4 times 10 to the negative 4. Let me show you the scratch work. 10 to the negative 4 times 10 to the 5th becomes 10 to the 1. Because remember, you add powers. And this becomes 10 to the 1, which is just 14 centimeters. Right? Because that's what's left standing. So on this scale, it would only be 14 centimeters. So the scale of the sun's diameter would be 14 centimeters using the 1 to 10 billion scale. Now let's scale the Earth diameter. Let's do the same problem. Up here in the problem, it says the Earth's diameter is about 12,760 kilometers. 12,760 kilometers divided by 10 to the 10th. So this would then become, well, let's see here. This is actually 1.2760 times 10 to the 1, 2, 3, 4, 10 to the 4th km over 10 to the 10th. Notice how I just converted it to scientific so I could do it quicker. Now we go here, boom, that's gone, and we're left with 10 to the 6th in the denominator. And this would become 1.2760 times 10 to the negative 6 kilometers. But again, we may not want to deal with it in kilometers. Let me see here. Geez, that's pretty small. That's a very, very, very small number. Let's try to convert this to millimeters, I guess, to make it sound a little bit better. So this is 1.2760 times 10 to the negative 6. You know what? I'm going to convert it over here. I'll even write it in green. So we're going to multiply this now by, 10 to the 6th millimeters to kilometers. Because this conversion I did over here was 10 to the 5th, and that was from kilometers to centimeters, right? Well, millimeters is over here, so we got to go one more. So this is just using the previous knowledge we had from that problem. And again, your test will be open note, guys. So you can definitely have, this stuff next to you while you're doing it. If you're worried you won't remember some of these conversions. So then this becomes, our final answer becomes 1.276 millimeters, right? Because this cancels with this. 10 to the negative 6 times, times 10 to the 6 would be 10 to the negative 6 plus 6, which is 10 to the 0, which is just 1, okay? So we have that. So the model of the sun at 14 centimeters in diameter is roughly the size of a grapefruit, and the model of the earth at 1.3 millimeters, so they rounded this off, 1.3 millimeters, is in diameter, is about the size of a ballpoint pen, or the ballpoint in a pen. So the little tip of a pen is about how big, the ballpoint in a pen is about how big the diameter of that is, compared to the grapefruit, which is the sun. So they're just trying to show you in the scale, it can still show you how drastically big or much larger the sun is in comparison, okay? Let's see here. Do I want to do this one? I felt like we kind of covered a lot. Yeah, I think that's okay, you guys. I'm going to go ahead and end the video for that. I feel like that's a good review. What I'd actually like to do is just real quick, before I end the video, I planned on showing you guys a few things. So if you took 3.2 times 10 to the 7th, and you multiplied this by 5 times 10 to the 6th, you're going to run into a problem whenever you do this, because, or let's say 3.1, because if you're asked to write the question in scientific notation, so they might say, write your answer in scientific notation, then what you need to do is you need to understand that when we do 3.1 times 5, 3.1 times 5, we get 15.5. So this is worth 15.5 times 10 to the 13th. And then some people are going to leave this as their answer. This is not scientific notation because there are two digits to the left of the decimal. So what you have to do is, I did it in a previous problem, but I just wanted to go back, is you have to write this as 1.55 times 10 to the, now you have to find a new way to write 15.5 as 1.55, and it still be worth the same. So I'm going to write this as 10 to the 1, right? Because if I multiply 1.55 times 10 to the 1, I will end up moving this right there, and that would become 15.5, just like above. But I still have this times 10 to the 13th, so I just attach that as well. So this becomes 1.55 times 10 to the 14th. So remember, when you're multiplying and the answer you get does not end up in scientific notation, then you fix it and you force it to be. So you do like a little scratch work on this guy and you write him in scientific notation. Then you attach the other part of the times 10 to the whatever, right? And that'll give you your answer. And this is in correct notation, right? They wanted scientific and I made it that way. Now it could go the other way as well. You could have 25 times 10 to the 5th divided by 75. No, let's do 50 times 10 to the 12th, okay? So this would actually be 1/2 times 10 to the, let's see, who's bigger? The bottom is bigger, so this is going to be gone. That's going to be 1, and this is going to end up with 10 to the 7th. So we're going to end up with a negative exponent, so times 10 to the negative 7. Okay, but remember, there's not really fractions in scientific notation, so I'm going to rewrite this as 0.5 times 10 to the negative 7. And now, just for a minute, I'm just going to focus on putting this part in scientific, and I'm going to leave this part later. So we're going to say this is actually 5 times 10 to the negative 1, right? Because 5 times 10 to the negative 1 would equal 0.5, and so I've done the same thing. But I still have to multiply times 10 to the negative 7. So then this will become 5 times 10 to the negative 8, okay? And this would be, once again, our correct answer. Let me write that a little bit better. Times 10 Just made it worse. 5 times 10 to the negative 8 would be another way to do this problem. Okay, so once again, if they ask you to write your answer in scientific notation, you got to be a little bit more careful. Okay, all right, you guys, thanks for watching. That's going to do it for this video.